It's my second Zoom seminar. The first I gave also this week, and also something I learned from my teaching on Zoom. I'm very bad in controlling my time in Zoom, so please keep me, in the time frame. I tend to speak too much on Zoom for some reason. So this talk will be based on a recent paper with Eviatar Sabag, who is my student. And it is also based on a series of papers we have written with several authors, Gabi Tzafrir, Eviatar, Hichol Kim, Kumrun Wafa, and others in the past 3 years. So I will mention the other works when it will be relevant in the talk. Okay, so I will be talking about SQCD and pair of pens. So let me start from a general introduction of what type of questions we are trying to ask and what do we want to do. So we are studying dynamics of four-dimensional supersymmetric quantum field theories. In principle, quantum field theories are interesting in many dimensions, but we are focusing in this series of works on 4 dimensions and on supersymmetric theories. On supersymmetric theories for obvious reasons, since we have a lot of control. And in 4 dimensions, because of what I'm going to tell you, or because of some nice things that you can do in 4 dimensions. So quantum field theories and supersymmetric quantum field theories in 4 dimensions exhibit a lot of very interesting phenomena, strong coupling phenomena, like infrared dualities, conformal dualities, emergence of symmetries in the infrared. And typically, as I said, this phenomena involve some strong coupling physics. So if you have, for example, an infrared duality, usually the statement is that you start from some UV CFTs, maybe some different looking UV conformal field theories, and then you flow to infrared to possibly some strongly coupled SCFT, and that SCFT might be the same for the 2 different UV descriptions. And also the symmetry that you see in the UV might be enhanced in the infrared. So there is some symmetry group that is preserved by your relevant deformation during the flow. And once you reach the fixed point in the infrared, the symmetry might be bigger. Okay, and also you have conformal dualities, which typically relate theories with weak coupling to theories with strong coupling. Okay, so we have a huge variety of examples of such behaviors. And one question that you might ask is there some organizing principle, how to understand all these phenomena, all these strong coupling phenomena in a unified manner, or try to predict new such dualities, in emergence of symmetry, and so on. Okay, so this is the big question we try to understand. And in recent years, starting, well, it's already not that recent, it's starting roughly in 2009 with the work of Gayotto, there is a way to think about such an organizational principle, and it goes through physics in 6 dimensions. Okay, so the way it goes is that you can geometrically engineer 4-dimensional supersymmetric quantum field theory starting with 6-dimensional SCFT, some 6-dimensional SCFT. Say an example which will be relevant for us today is an E-string theory, which is an SCFT, 1,0 SCFT, which has some flavor symmetry. In this case, it's E8. And you take that SCFT, you choose an SCFT in 6 dimensions, you put it on a compact space, on a Riemann surface, you turn on some possibly background fields for various background fields that you can turn on. So, for example, you can turn on fluxes for your global symmetry, and then you flow to 4 dimensions. Basically, you look at your theory below the energy scale set by the surface, so you get some effective 4-dimensional theory. That 4-dimensional theory is UV completed by construction by your 6D SCFT, and possibly there is a 4-dimensional theory which flows to this effective theory, and typically you can find UV complete 4D theory which flows to the same effective theory or an SCFT in the infrared. So this is a geometrical engineering of 4-dimensional supersymmetric field theories, and you can ask, why is it useful to discuss strong coupling effects and so on? So the usefulness of this geometric engineering stems from the following fact. So typically, when you try to understand this map between 6D constructions and 4D theories, you can do it in steps. Okay, so you can first understand the compactifications of 6D theories on some simple surfaces, so on 3 punctured spheres or 2 punctured spheres with flux. And once you understand these basic building blocks, you can also understand how to combine them together to build theories corresponding to compactifications on more complicated surfaces, like genus G surfaces and so on. Okay, so basically you are breaking the problem of understanding compactification on a big surface, on some genus G surface, to understanding compactifications on small Lego pieces, and then you learn how to combine those pieces, and you can construct field theories, a wide variety of field theories in 4 dimensions using these building blocks. Now, the point is that this breaking of the problem into pieces has some choices. Okay, for example, you are breaking a given Riemann surface into a pair of pens, and you have choices how to do so. You have a flux corresponding to this Riemann surface, and you can choose how to associate flux to different pieces in this decomposition. And these choices should not matter for the physics you get in 4 dimensions. Geometrically, it's maybe obvious, but in 4 dimensions, it leads to highly non-trivial statements about dualities and emergence of symmetry and so on. And we will see examples today. Okay, so this is the general framework of what I'm going to tell you about. Is there any question about this introduction? Okay, so let me start with an example of a curious 4-dimensional quantum field theory fact that we will try to explain using such a geometric engineering program. So one can start with the theory that I mentioned on the previous slide, an E-string theory, which has an E8 symmetry in 6 dimensions, and compactify it on a genus G Riemann surface with genus bigger than 1, and not turn any background field. So no fluxes, nothing, just compactify this theory. So one thing you can do when you do that is you can predict what should be the anomalies, the A and C anomalies, the conformal anomalies in 4 dimensions. And you do that by taking the anomaly polynomial of the E-string theories in 6 dimensions, which is known, and integrating it over the Riemann surface. And you can generate easily a prediction for these anomalies, and they are written here. So this is an A and the A and the C anomaly of a quantum field theory that you should get in 4 dimensions. And the question you can ask is, what is that quantum field theory? Can you describe this quantum field theory directly in 4 dimensions? And can you do that using a Lagrangian? And then you can make a very wide assumption that you can do so with a conformal gauge theory. Okay? It doesn't have to be true. Usually it is not true that you can describe theories which you get in these compactifications by conformal gauge theories, but you can ask this question and see if you can find such a theory. The fact that you assume that the description is conformal means that all the fields, all the chiral superfields that you have in 4 dimensions should have free R charges. So you basically assume that the R charges of all the fields are 2/3, and you assume that all the beta functions for the gauge interactions and the superpotential interactions vanish. Okay, so you have a conformal field theory, and example of such a theory is, of course, n equals 4 super Young. Now, in 4 dimensions, there is this nice relation between A and C anomalies and the 't Hooft anomalies of R symmetries. Okay, so you will know what the A and C anomalies are from this formula, and we know that, or we assume that the chiral field should have R symmetry, which is 2/3. Then basically, what these two equations encode is the dimension of the representation of the matter and dimension of the gauge group. So what contributes to these anomalies are the gauginos and the fermions in the chiral multiplets, and we assume that we know there are charges, so we can read off from these two equations the dimension of the gauge group and the dimension of the representation of the matter. So with these particular anomalies, it turns out the dimension of the gauge group is an integer, and the dimension of the representation is an integer. And you can view this as a sign that there might be such a conformal gauge theory description. If these numbers would be fractional, then this assumption is clearly wrong, okay? And now you can start going over conformal gauge theories in 4 dimensions and see whether with this dimension of a gauge group and this dimension of representation, you can, whether you can find a theory which is conformal, okay? So for example, you can look at G equals 2, and then dimension of the gauge group should be 16. There are not too many groups that you can build such that the dimension is 16. One such choice is SU3 squared, so 2 SU3 factors. And just going over all the possibilities, you can easily find such a theory. So here is an answer for a genus G surface, compactification on genus G surface. So it turns out that if you take a gauge theory, such a quiver theory, which has 2G minus 2 factors of SU3 gauge symmetry, and this pattern of bifundamental and fundamental fields, this theory is conformal. Each SU3 has 9 flavors. So it's at the edge of the conformal window. Typically, at the edge, we get an IR-free theories. We get the one loop beta function vanishes, but the gauge coupling is marginally irrelevant. But for SU3, since you can turn on baryonic superpotentials, which are also marginal, you can build a conformal manifold. You can find, you can turn on both gauge couplings and superpotential couplings and construct exactly marginal deformation. So this theory is conformal. It has exactly these anomalies, ANC anomalies. The global symmetry that you see in the Lagrangian is SU9, and SU9 is a maximal subgroup of E8. And actually, the claim is that somewhere on the conformal manifold of this theory, this rank 8 symmetry, the cartons of this SU9 enhance to E8. And this you can, for example, see by computing various quantities like supersymmetric index, and seeing that all the protected states or protected operators in this BPS operators in this theory come in representations of E8. For example, the way it goes, you get for the marginal operators, you get marginal operators which correspond to triangles of this quiver, and these are in 80 plus 1 representation of SU9. So you have 9 times 9 bar, so you have 80 plus 1. And then you have baryonic operators and anti-baryonic operators, which give you 84 and 84 bar. 80 plus 84 plus 84 bar is 248 of E8, and you always get such combinations. And if you compute the dimension of the conformal manifold of this quiver theory, you get that it is equal to 3G minus 3, which you can associate with the complex structure moduli of the surface, and G minus 1 times 248, which you can associate with the different flat connections that you can turn on this surface for the E8 global symmetry, okay? So this is an example of kind of a random field theory fact that if you look at this type of a theory, you have an SU9 global symmetry, but somewhere on the conformal manifold, you have a claim that the symmetry enhances to E8. And the question is why, okay? Nothing in what I have discussed here explains why is it so, or gives a hint why should it be so, okay? So
I have a question.
Yes.
So what is this double line, the right? So you have 2 bifundamental, you mean?
That's right.
Okay, I see.
So so this is 1 bifundamental, and these are just 2 bifundamentals.
Oh, okay. And
you have 3 fundamentals and 6 fundamentals here. So in total, you have 9 fundamentals, and then 9 anti-fundamentals.
And do you have superpotential, cubic superpotential in this triangle?
Right. So we have the superpotential is a cubic superpotential for each triangle. And we have also the baryons are marginal operators. So you turn on baryons for all the edges of this circle.
Yes.
Okay? And in principle, you can also turn on baryons for the spikes of this wheel. If you turn on these baryons, you will break the SU9 to a subgroup. Okay?
I see. And here, there's a 6 SU3 gauge group.
That's right. So this is genus
this corresponds
4.
to genus 4. Okay, I see.
Yes, it should be this. These 2 pictures should be correlated.
Yeah. Okay, thank you very much.
Okay. Okay, so the question we will ask is why why this theory corresponds to this compactification and how to understand it in terms of this geometric engineering of taking blocks which correspond to three punctured spheres and gluing them together. Okay. Let me give you the answer right away. What is the building block that you need to use to construct this type of equivalent? And then we will discuss how one proceeds to check this claim and generate a new understanding from this decomposition. So this is a kind of an isolated fact. We will break this picture into pairs of pens. And once we will understand how to compose this theory with pairs of pens, we'll be able to construct other theories which have other symmetry enhancement or symmetry emergence properties and duality properties and so on. So by understanding this kind of a fact, we will be able to generate many other facts. Some of them are known and some of them are somewhat novel. Okay, so this is the answer. So the answer to the problem is that the basic building block of the construction of geometric construction of this type, if you start from E-string theory and you compactify E-string to 4 dimensions on generic Riemann surface, you can first compactify on a 3-punctured sphere with some value of flux, and we will discuss the flux in a moment. And the theory that you will get is just SU3 and F equals 6 SQCD. Okay? SU3 and F equals 6 SQCD has a global symmetry group, which is SU6 times U1 baryon. So SU6, which rotates, say, fundamentals, and SU6, which rotates the anti-fundamentals. We split the SU6, which rotates the anti-fundamentals, into 3 factors of SU2 and 2 U1s. Okay, and these 2 U1s and U1 baryon we denote by this U, V, and W. These are 3 U1 symmetries that we have in the problem. And we associate the 3 SU2s to 3 punctures. So at the level of this gauge theory, it's a bit artificial breaking, viewing this theory in a little bit artificial way. But we'll see that it is a natural thing to do. Then we assign non-anomalous R symmetry to the fundamentals to be 2/3 and to anti-fundamentals to be 1/3. This is not the superconformal R symmetry. The superconformal R symmetry here is a half, but it is again a convenient choice of R symmetry that we will see will play a more fundamental role in what follows. Okay, so this is the theory we associate to the 3-punctured sphere. Now, another interesting fact about this decomposition that I want to mention is that each SU2 we associate to a puncture has a natural set of operators associated to it. And I call these operators moment map operators for a reason I will explain on the next slide. So these operators are in fundamental representation of each puncture SU2. So for example, looking on this green SU2, we have these operators called MU here. They are in fundamental of this group. And there is a 6th set of them, which are the mesons. Okay, this is these 6. And there are also 2 baryons. And the baryons you can construct by taking this, say, antiquark and this antiquark square. So these are antibaryons in this language, or this one and this one squared. These are two baryons, which are singlets of the SU3 gauge symmetry group. And they are objects in the fundamental of this SU2. And you can do the same for any other SU2 symmetry that you associate to the punctures. You have more baryons. You have actually 20 baryons here, or 20 antibaryons here. So these types of baryonic operators that I discussed amount for 12 of them. And you have 8 more, which are in tri-fundamental of these 3 SU2s. This tri-fundamental will not play a role for us. Okay. So this is the theory, and this is the way I want to view it. And these moment map operators with this assignment of R charges have all R charge 1. Okay. So now let me explain why these facts that I mentioned, the fact that you have an SU2 symmetry associated to a punctures, and these moment map operators, why these facts are important and where do they come from. So for this, I need to explain to you how to think about punctures on the Riemann surface when you compactify from 6 dimensions. So a way to think about a puncture is to take your Riemann surface with a puncture and elongate the puncture to form a long cylinder with a boundary at the end. And then you first consider, reducing on the circle which goes around the cylinder, and then you get some effective 5-dimensional description. And the point is, if you turn on certain holonomies around this circle, sometimes, not always, but for some choices of 6-dimensional theories and some choices of holonomies, you can find an effective 5-dimensional description, which is a gauge theory. Okay? And with some gauge group G. For example, if you take 2,0 theory and you do that, you get an SUN maximally supersymmetric Yang-Mills theory in 5 dimensions. And if you take the E-string theory that we are discussing now, you get an SU2 gauge theory, n=1 SU2 gauge theory in 5 dimensions with eight octet of flavors. Okay, now when you, since we have a boundary and we want to preserve some supersymmetry, we need to put some supersymmetry preserving boundary conditions. And there is one such boundary condition which basically freezes the gauge group at the boundary. We give Dirichlet boundary conditions for the vector fields and Neumann and the Dirichlet boundary conditions for other fields to preserve supersymmetry. And what happens is that this 5D gauge symmetry is frozen to be the 4D some flavor symmetry. And this is the flavor symmetry which is associated to the puncture in 4 dimensions once you continue flowing to 4 dimensions. So in the case of 2,0 theory, the flavor symmetry associated to these maximal types of punctures, these types of punctures are called usually maximal, is SUN. And you also give Neumann boundary conditions for some of the fields, and the fields here are in the adjoint representations, and so you get a certain natural operators in 4 dimensions which are charged under this puncture symmetry, which are in the adjoint representation, which in this context are called moment maps, and they come in the same multiplet as the conserved currents. In this case, you have n=2 supersymmetry in 4 dimensions, so these are the moment maps of the puncture symmetry. In the case of the E-string, again, the flavor symmetry associated to the puncture is SU2 because of this logic, and you have an octet of chiral fields which will be charged in the fundamental representation of this SU2. This will be the natural objects in 4 dimensions, and by analogy with the 2,0 theory, I will call these operators moment maps. The supersymmetry here is only n=1. So it's just the same name, but it's not the same type of object. Another thing I need to say that there are choices of boundary conditions of like which components you give Neumann boundary conditions and which you give Dirichlet boundary conditions. So out of these 8 hypermultiplets, you in some sense you pick 8 chiral fields, and there are some choices. So there are some choices you are making. And this is related to the fact that on this slide, I have colored the different punctures with different colors. So these are, all of them are SU2 maximal punctures, but they are not the same. You can see that they are not the same because the pattern of charges under this triplet of U1s of each of the moment map operators is different. And
so
in this
what are the UVW?
These are the fugacities for the 3 U1 symmetry. So okay, I denote we have a U1U, U1V, and U1W.
I see.
And these are the, you can read of the charges from the powers of these fugacities.
And the XYZ are the fugacity for SU2?
For SU2, okay. Yes, for each one of the puncture SU2s.
Okay, thanks.
So these are the these are 3 different types of punctures. All of them are maximal, but they are not the same. Okay. And this octet of natural operators, we want to identify with these operators we expect to come from 6 dimensions, okay? So that's how we should think about these theories. So this is a claim, and now to check this claim, we need to combine from these building blocks theories which correspond to higher genus Riemann surfaces. And to do so, we need...
Sorry, I have a question.
Yes.
The 5D, I'm a bit confused. The 5D gauge theory has SU2 gauge symmetry, but the 4D, right. And this is supposed to be the 4D global symmetry, which is E8.
That's right. Because you have a boundary and you put a Dirichlet boundary condition on the boundary. Basically, you freeze the gauge symmetry degrees of freedom. That's how you should view it. Okay.
But I thought that the gauge symmetry becomes the global symmetry of the 4D theory, but that's here right. The gauge symmetry is SU2 and...
and the flavor symmetry associated to the puncture is also SU2. Maybe I did not understand.
Okay, okay, yeah, sorry. Yeah, I understand.
There is other symmetry. So there is this E8 symmetry, which you start from 6 dimensions, and it is broken to some subgroup by the fluxes, which I did not discuss yet, and also by these choices that I mentioned of what type of, you know, which fields in 5 dimensions you give Neumann and which you give a Dirichlet boundary condition. So there is this rank 8 symmetry, which is broken to something. It comes from 6 dimensions. But in addition to that, each puncture gives you an SU2 symmetry.
Okay, thank you. Okay.
So now what we need to learn is, what we need to understand, as I said in the beginning, is what are the building blocks, but also how to combine building blocks together. And to combine building blocks together is to take, say, punctured Riemann surfaces and glue them to form, like glue them along the punctures. And here there are 2 procedures that you can do, which we call S-gluing and phi gluing. And basically, these procedures are to undo the effect of this, of putting these boundary conditions. So what you should do when you glue in 4 dimensions 2 theories together, you should make again these gauge fields dynamical. So you gauge the symmetry, the global symmetry. In this case, it's SUN. In the case of 2, 0, in the case of the E string is SU2. And you also need to reintroduce the fields that you have thrown away, say, by Dirichlet boundary conditions. Okay, so let me explain what are these 2 ways of gluing. So let me start with the simpler one, which we call S-gluing. And again, this story is very analogous to class S. It's a very generic story for any type of compactification. We will apply it to the E-string case here. So we take 2 punctures, which are of the same type, and we take the diagonal combination of the SU2 symmetry corresponding to the 2 punctures, and we gauge it. And we take the moment map operators associated to the 2 punctures, and we couple them through the superpotential like this. Okay, so basically, if you wish, what we do is we think of the octet of fields which we given a Neumann boundary condition on one side, associated with the fields which we given a Dirichlet boundary conditions on the other side. And then in this way, we complete the full spectrum of fields that we have in 5 dimensions. So 1 octet comes from here and 1 octet comes from the other side. Okay, and in this way, you undo the boundary and you glue 2 surfaces together. Okay, and here are the 2 trinions that we had on 2 slides ago when we glue them in such a way. So we take one of the SU2 puncture symmetries and we gauge it, and we turn on a certain superpotential. Okay, which is basically this superpotential, where I identify the mesonic moment map operators, and there is also superpotential, which is sextic, which identifies the baryonic baryonic moment maps, which I don't know how to write in the quiver notations, but there is also a sextic superpotential. There is interesting dynamics that I will not discuss here. I will discuss a little bit later. Okay, is this clear?
Yes.
Okay.
Yes.
Okay, so now next what we do, the basic claim is that that's it. We understand how to glue things together. We understand what are the basic building blocks. So now what we want to do is to recover this picture. Now we have these 3 punctured spheres. We want to glue them together to form a closed Riemann surface. Another thing I want to mention before doing that is that there are fluxes associated to the Riemann surfaces, which I postpone to talking about. But the point is, when you turn on such a superpotential, you identify the symmetries of one theory with the conjugate of the symmetries of the other theory that you glue together. Say if this moment map is charged +1 under one symmetry, then this moment map will be charged -1 under that U1 symmetry. So if, say, one of the trinions is charged, it has flux plus flux in some U1, the other will naturally have a charge minus flux. So the flux you would associate to the whole theory will be 0. Okay, so let us analyze this gauge theory. This gauge theory is very simple. If you look at this SU2 gauge node, it has 3 flavors. Okay, and we know that SU2 with 3 flavors has a very simple Seiberg duality. Okay, it basically is described in the infrared by a Wezumino model of its mesons and its baryons. Okay, so here is this statement of Seiberg duality, slightly generalized as we will use it later on. So this case is of n equals 1, but let us discuss it for general n. Again, we have an SUN plus 1 gauge theory with SUN plus 2, sorry, with n plus 2 flavors. And this theory is equivalent to this Wezumino model, where these fields are the mesons, and these are the baryons and the antibaryons. Okay, so this type of a triangle here, which this type of a line which appears here, we can exchange with this triangle. So we had a 6 here, and when we perform Seiberg duality on this line, we can, it's the same picture without a gauge group, and the 6 turns into a 7. Okay, is this clear? Because
yes.
Okay. So what we've done now, we glued the 2 3-punctured spheres along one of the punctures, and now we can continue doing so. We can glue these 2 types of punctures with the same procedure. When we do so, we will get another bifundamental, and this 7 will turn into an 8. And when we glue these 2 punctures, we again add a 3rd bifundamental, and this 8, the 7 will turn into, which turned into an 8, will turn into a 9. Okay, and we will get exactly this type of picture when G is equal to 2. We get two SU3 gauge groups and 3 bifundamentals and an SU9 global symmetry group. And in more generality, we can take 2 such trinions together, glue them to form a torus with 2 punctures, and then glue this tori in such a circular manner, and the quiver you will get is exactly this wheel. Okay. So this is a way to decompose what we have discussed till now. This is a way to decompose this type of theory into pair of pens and gluing of pair of pens. And as I have mentioned, since we are gluing each the torus with 2 punctures, we glue with this S gluing. Each one of these tori has 0 flux associated to it, so the combined surface will have a 0 flux associated to it, matching the construction that we had, the kind of guesswork type of construction we had when we built this theory. Okay, so this is the basic understanding, and from it now we will build new dualities, new instances of emergence of symmetry, and then we will generalize this statement. Here we had the group being SU3, and you can ask what happens if you want to discuss theories with higher end gauge groups and so on. Okay. So let me now complete this picture by discussing what is the flux associated to each one of these trinions. So till now, what we did, we said that there is some flux, but we kind of canceled the effect of the flux by this procedure of S gluing, and you can ask what is the flux associated to the trinion. And to do so, we can do another type of a gluing, again, very analogous to what you do with 2, 0. So again, you take 2 surfaces, you take 2 punctures, you gauge the diagonal combination of the puncture symmetries, which in this case is SU2. But now you identify the fields you gave Neumann boundary conditions with the fields you gave Neumann boundary conditions on the other side. Okay, and the way you do so, you introduce new fields, chiral fields in 4 dimensions, which are these phi's, and you couple them to the moment map operator. So this procedure is often called flipping, and I will refer it to as flipping. So we flip the moment map operators. In the case of 2, 0, these phi's are the joint chiral superfields in the n equal 2 vector multiplets. Okay, so in the n equal 1 language, these are not coming from some extra supersymmetric vector multiplet, but these are the fields we add by hand when we glue 2 punctures together. Notice that here the symmetries of these 2 moment maps are the same. They are opposite to these phi's, but they are the same. So if we associate some flux to one theory, to one copy of the trinion, we should associate the same sign of flux for the other copy. Okay, so then we get the theory we get is drawn here. It's a little bit more complicated. So these red fields that I denote here are these fields phi. So we have 6 fields corresponding to these mesonic moment maps, and these dotted lines, they flip the baryonic moment maps. So this dotted line flips the field which is built by this field times this field squared. Okay, So it's not a cubic superpotential, it's a quartic superpotential actually. So I don't know how to draw it, whether there is a common notation for that. So that's what this dotted line means. They flip these are chiral fields which flip the baryonic moment map operators. Okay. Now look at this theory, and for this theory, I want to discuss a little bit the dynamics. It's actually non-trivial. So if you look on this SU2, now it has 14 fundamental chiral fields coming with it. Okay, so you have 6 coming from here, you have another 6 coming from here, and you have these 2 fundamental fields. So you have the number of flavors is 7. So if you consider this gauge theory in isolation, it looks like as if it is IR-free. And also you have the quartic superpotentials and you have cubic superpotential, and you should worry whether they are relevant or irrelevant deformations. Okay, so the dynamics of this theory of this gluing is non-trivial, but the claim is that there is a way to make sense of this dynamics by analyzing it in steps. So there are different types of deformations you turn on. You can turn on the cubic superpotential, which is flipping of the mesonic moment maps. You have the gauging, and then you have a quartic superpotential, which is the flipping of the baryonic moment map. So you can first turn on the cubic deformations, then flow to infrared CFT. Then at that point, the gauging actually becomes asymptotically free, though at the UV it was infrared free. Then you can gauge the SU2 symmetry. Then you can turn on a quartic superpotential, which actually turns out to be exactly marginal at this point, and you arrive at an infrared CFT. So although this theory looks like it has irrelevant deformations, there is a sense, you can make sense of it as an UV complete theory in 4 dimensions, again, analyzing the deformations one by one, okay? And usually these types of deformations are called dangerously irrelevant deformations. Things which look irrelevant in the UV, but actually when you start flowing, they become relevant or exactly marginal deformations, okay? So this is this other way of gluing things. And since we now identify the fluxes of the 2 trinions to be the same, we can glue these 2 trinions again into a genus 2 Riemann surface and see what type of a theory we get. Okay, this should correspond to compactification of the E-string theory on a genus 2 surface with some value of flux. Okay? So we do that. We have a field-theoretic description. We can compute A and C anomalies. In this case, these A and C anomalies are some not very ugly, but not very trivial numbers. And you can ask whether there is a compactification of an E-string theory on a genus 2 surface with some value of flux, which gives exactly such anomalies. And indeed, there is a way to get these anomalies. For example, if you turn on a flux in a U1 inside the E8, which breaks the E8 to E7 times U1, you turn 1 unit of flux in that U1, you exactly get such anomalies. And that means that since we took 2 trinions and we get 1 unit of flux, each trinion should be associated with half a unit of flux in this normalization. And the breaking of like the decomposition of E8 into E7 and other symmetries is like this. So we have E8 breaking into E7 times SU2, and the flux is in the cartan of this SU2. And then we think about this E7 as SU6 times SU3 maximal subgroup. This is the SU6 which rotates the fundamentals that we see in the quiver, and the cartan of this SU3 together with the cartan of this SU2 are the 3 U1s that we see in the quiver. So again, in the quiver, we see some subgroup of this E7 times U1, but once we combine things together, we get a theory which should have an E7 times U1 symmetry. Okay, so this is a new fact that we derive by understanding this decomposition. We can also see this enhancement into E7 by computing certain quantity, for example, the supersymmetric index, and you see that everything falls into representations of E7. Moreover, the numbers that you see here, the multiplicities of different operators, are not just some random numbers, they're actually also given in terms of the flux. You need to do some clever, not so clever, somewhat standard Riemann-Roch reduction of operators, of simple operators from 6 dimensions, and you get these types of multiplicities, and in general, they also match. Okay, so you basically take the stress energy tensor and reduce it, and you get the complex structure moduli, and the reduction of the conserved currents gives you other marginal or relevant operators that you see here. This is a side comment. Please ask me more if you are interested in understanding this better. Okay, so this is the basic dictionary. Any questions about that? Okay, so let me continue now. Now we have these building blocks and we know how to combine them together. So now we can ask what is the physics that we can extract from it. So we have these three punctured spheres. So one thing that we learned from class S constructions, that we can get interesting dualities by gluing things into 4 punctured spheres and considering different pair of pants decompositions. So 2 pair of pants decomposition should correspond to a duality of the theory. So for example, here we glue 2 3 punctured spheres together as we did before, we get a 4 punctured sphere with 4 punctures. And there should be a duality exchanging the 2 types of punctures. Since we glue things together, just as gluing the 2 punctures have opposite charges under U1 symmetries, so we can make the 2 pairs of punctures to be exactly of the same type by flipping the moment maps of corresponding to each puncture. And then, for example, you can test the duality in the index computations by exchanging the fugacities corresponding to the punctures in that computation. Because there is a duality and the index doesn't know about the couplings, the index should be invariant under this exchange. So this implies certain non-trivial facts about index computations, and you can check this duality, at least at the level of the index, and you find that indeed things are consistent. And we will see a little bit later on that this duality, this pair of pants duality, although it looks far from that, is a generalization of Intriligator-Pouliot duality discovered in 25 years ago for an SU2 gauge group, and we will see how it comes about. Okay, so you can derive various. Yes,
please. This is
yes.
Nopado. Hi.
Hi, Nopado.
I was wondering. So you show the enhancement of symmetry for the phi gluing, right? And is there enhancement in case of S gluing also?
In the S gluing, there is an enhancement to E8. After you glue things into into a closed Riemann surface, and say you compute the index, you see that everything forms E8 representations.
I see. For the phi gluing, you have E7.
For the phi gluing, we have an E7 times U1, and that means that there is something which broke an E8 to E7 times U1, and that something is the flux that we turn on.
Okay, thank you.
And the value of flux is consistent with the anomalies and with these multiplicities that appear in the index computation.
Okay, thank you.
Okay, so there are these pair of pants dualities, but actually you can do more fun things with this type of theories. So to build these more fun types of dualities and symmetry enhancements, we make the following observation. So I was talking about the flux, and we have 8 U1 symmetries, which are the Cartan of E8. So in principle, we can turn on 8 fluxes flux for each one of these U1s. So to do so, we need to choose some basis of these U1s, of these Cartans. We have a natural such a basis since we have 8 moment map operators. Each such moment map operator is charged under a different U1. So we can identify this octet of U1s with some combinations of the Cartans of E8. And we can turn on fluxes in each one of these U1s. So in general, we should think of the flux as an octet of fluxes. Each flux is for each component of such a U1. In this language, for any 3 types, we have 3 types of punctures, so it doesn't matter which one you choose to define your U1s, the flux vector turns out to be this -1, and 6 zeros, where I order this octet of symmetry such that the 2 first symmetries are the symmetries of the baryonic moment map operators, and the rest of the 6 are the mesonic moment map operators, are the U1 symmetries of the mesonic moment map operators. And indeed, this type of flux preserves his 7 times U1, and there is a simple group-theoretic way to compute what is the symmetry preserved by each vector of flux, which is written here. Okay, so, and again, I want to stress on this slide that the choice of basis is given by a choice of puncture. You can choose any type of puncture, then you might get a different value of flux. You get different combination of the U1 cartons of the A8, but things should be related to each other by Weil symmetry, as we will see in a moment. Okay, so given this understanding that we have an octet of fluxes and each moment map operator is charged under one of the U1s, we can do another natural field-theoretic procedure. So one procedure we did was combining punctures by gauging the diagonal combination of a symmetry, but we also can do something which is called closing a puncture. So the basic statement is like that. If you have a surface with a puncture, it has a symmetry and it has a moment map operators which are charged under that symmetry. We can take one of the components of these moment maps and give it a vacuum expectation value. And also the technical details are that you need to add some chiral fields and flip some of the other moment map components of the moment map operators. But the basic statement is that after you do that, you get a theory which corresponds to compactification on the same surface, but the puncture removed. And the flux that you associate to the new surface is shifted relative to the flux of the original surface. And the shift of the flux is just in the symmetry of the moment map you gave a vev to. Okay, so this is the statement you can derive by just doing this field-theoretic operation and seeing what type of theories you get and matching to six-dimensional predictions. Okay, so this is the basic statement. So in our case, we have this octet of moment map operators. Some of them are baryonic, some are mesonic. And the vector of fluxes is like that, -1, and all zeros. So we can do this operation and close, say, the puncture, a given puncture, giving a vev to a baryonic moment map. And then we shift the flux in such a way, and we get this value of the flux. Instead of -1, we get a 1 -1. Which turns out to be, again, an E7 times U1 type of flux. So we started from a 3-puncture sphere. We end up with a tube with 2-puncture sphere with a 7 times U1 flux. We can also give a vev to one of the mesonic components. Then the theory we would obtain is different. We would obtain this type of flux. So it's -1, all zeros. We add now a 2 to the mesonic component. So we get this type of flux. And this flux preserves only E6 times SU2 times U1. Okay, so this is at the level of these fluxes, what we expect. But we actually have a very concrete field theory. We have this SU3 SQCD. So we can do these flows. We just are flipping, we are just giving vevs to some operators and adding some flip fields. So it's a completely well-defined field theoretic operation we can do. For example, giving a baryonic vev, we Higgs completely the SU3 gauge symmetry, and we get some Wess-Zumino model. So it's a theory of chiral superfields, which is drawn here. These two SU2s correspond to the 2 remaining punctures. So in terms of the original puncture that we closed, the flux is like that. In terms of the symmetries associated to the other punctures, we have different vectors of fluxes, but all of these 3 are equivalent, and they are related by Weil symmetry of E8. Okay. Now we can take these tube theories, a pair of such tube theories, and glue them into a torus. And we obtain a closed Riemann surface with flux. And this theory should exhibit represent E7 times U1 representation, as it indeed does. For the mesonic vev, we Higgs the SU3 symmetry down to SU2. So we get a different type of a theory. The SU2 here has 5 flavors. Again, we can think about the flux in these different ways. We combine 2 such tubes together, and we get this type of a quiver theory, and it should have E6 times SU2 times U1 symmetry, as indeed it does. If you can check it by, again, computing indices and so on. And this type of statements we derived with Hichol, Gabi, and Kumrun about 3 years ago in completely different way. Okay, not by closing punctures of a Technion, but by figuring out what the tube theories are by themselves. Okay, so it actually, what I'm telling you now matches what we have obtained with these co-authors 3 years ago. Okay. Any questions about this? Okay. So let me continue, and with this game of giving vevs to moment map operators, you can play a lot of games. So let me give you an example of another game that you can play. As I told you, you have these moment map operators, and you can actually flip the moment map operators by introducing some gauge singlet fields, and that flips the charges under the U1, which is associated to that moment map operator. So basically, in the vector of fluxes, you would flip the sign of the flux corresponding to that component of the moment map operator. So for example, if you flip one of the mesonic components, since the flux is 0 in mesonic moment maps, you don't change the value of the flux. Then you can again close the puncture by giving a vev to the new moment map. The new moment map is just a field. So you give a vev to a field, which is the same as giving a mass to the mesonic operator. You just turn on a quadratic superpotential, which is a mass term for one of the flavors. So the flux is exactly the same as the mesonic vev we had here, but the field-theoretic operation is very different. You give a mass to a mesonic operator instead of giving it a vev. So what you will get is actually SU3 theory with 5 flavors. You get a different gauge theory. And then you can ask, well, if this geometric picture is consistent, the two operations should be the same. And luckily they are the same, because SU3 with an f equals 5 is Seiberg dual to SU2 with an f equals 5, modulo gauge singlet fields, which should also work out. And they indeed work out, okay? So this is a geometric way to understand Seiberg duality, if you wish, a very well-known Seiberg duality. We can do the same operation also for a baryonic moment map. We can flip one of the baryonic moment maps, and then we change the value of flux to this, okay? And then we close the moment map, we close the puncture by giving a moment map to this component of the octet of moment maps. And now we get a different value of flux. This flux actually preserves an SO12 times a U1 square symmetry. So it's not one of the symmetries we obtained before. You can analyze what happens field theoretically. So here we flip a baryonic operator and give a vev to a flip. So we just turn on a baryonic superpotential for SU3. We don't get rid of any flavors, and we don't Higgs anything. We add the gauge singlet fields that I mentioned on the previous slide, and we add some superpotential. So you get a theory like that. And the point here, the nice point here is that you can use actually these types of trinions, these types of tubes, which preserve E7 times U1 symmetry, and glue 3 such tubes together to combine, to build a tube which has the same type of flux, which preserves SO12 times U1 squared. So you just glue 3 such tubes together with various combinations of S and phi gluing, and you obtain a theory which corresponds to this vector of flux. And it turns out that this flux is while equivalent to this type of flux. So that means that if you take this theory, which is obtained by gluing 3 tubes together, E7 tubes together, and glue from 2 copies of it a closed Riemann surface, a torus, it should be equivalent to taking 2 copies of these theories and gluing it together. So this is a novel type of a duality you get. Okay? I don't know, maybe by thinking hard enough, you can reduce it also to Seiberg duality. I don't know how to do it, but maybe it's possible. Okay? Any questions about this? How I'm doing with time, and how much do I have left?
You have like 6 more minutes, but if you want to continue, I mean, you can continue as you want.
So let me take, sorry?
May I ask a question, please?
Yeah, sure.
See, yes, there's a previous slide you have first regarding notation. What they mean by 2 and 3, it's a trifundamental or in the right diagram?
In the right diagram?
Lower one, yes,
oh,
that one.
No. This is okay. This is, think of it as these 2 SU2s is the same SU2 flavor symmetry group, which like think of this quiver drawn on a sphere, and this SU2 is at infinity. Like I could draw a line like that, and this an SU2 flavor symmetry here, like as a square usually.
Oh, I see. Okay, you identify them.
Like, Yes, and these crosses are flip fields for the baryonic operator.
Okay. And the other one is the slide after that you have. Yes, so you have box, the orange box with 1. So do you interpret this as another puncture or?
No. These ones came from the like we closed that puncture. We had 3 punctures, orange, green, and blue, and we closed the orange puncture. And these are the fields which are left from from
closing the orange puncture.
From closing the orange puncture. Yes. So only these 2 SU2s are associated to the puncture. These are leftover fields from closing.
Okay, thank you.
Okay, so let me take 10 minutes and what I will do, I will generalize this picture of a string to higher rank. Okay, so please feel free to stop me at any point.
Okay.
So what is the generalization? So we discussed how an SU3 gauge, like set of SU3 gauge theories, some quivers that you can build, is related to E-string compactifications. And you can ask, well, this is a very special statement. What about other like SQCDs with other ranks? Okay, and actually there is a nice generalization of the story, a simple generalization. So you can think of E-string theory as a theory residing on a single M5 brane probing a D4 singularity. Okay? And this SCFT has a generalization to a single M5 brane probing a Dn+3 singularity. The global symmetry of this SCFT in general is SO4n plus 12. For n equal 1, it is E8, SO16, which enhances to E8. Okay? And all this construction really makes sense for n greater than 0. For n equals to 0, it's a D3, which is the same as A3, and it's believed to be a free theory. Okay, so in this construction, we take n to be bigger than 0. And this type of SCFTs are called minimal Dn+3 conformal matter theories by Michele Del Zotto, Jonathan Heckman, Alessandro, and Kumrun from 2014. Okay, so we now can try to generalize the statements that we had for this class of theories, labeled now by n. Okay, and the generalization is rather straightforward. So here is the basic statement. So if you take an SUN plus 2 SQCD in the middle of conformal window, so you take an f equals 2n plus 4, okay, and n equals 1 is the case we analyzed before. The statement is that you get a Technion, which you obtain by taking this D-type conformal matter, minimal conformal matter, and reducing on a 3-punctured sphere, such that you have 2 maximal punctures with SUN plus 1 symmetry and 1 minimal puncture with SU2 symmetry. And I will explain a little bit on the next slide where this comes from. The global symmetry of the theory is SU2n plus 4 times U1 baryon. Again, we take one of the SU2n plus 4s and break it into SUN plus 1 times SU2 and 2 U1s. And we keep other SU2n plus 4 as a global symmetry. And the statement is that this SU2n plus 4 times the 3 U1s that we have is a subgroup of SO4n plus 12 global symmetry of the 6D theory. And these symmetries are puncture symmetries. Again, we have, for each puncture, we have a collection of moment map operators in the fundamental or anti-fundamental representation. So these are for maximal puncture, and these are for minimal. Again, each one of them is built from 2n plus 4 mesonic operators and 2 baryonic operators. Okay? And here there are many more baryons that we can build, but they don't play a role in what I'm talking about. And we can do exactly the same types of games we played before. So let me just mention what are the punctures here. So the punctures here come by compactifying this 6D theory on a circle down to 5 dimensions. And you can get one description in 5 dimensions, which is an SUN plus 1 gauge theory with 2n plus 6 flavors. So that's where SUN plus 1 symmetry, global symmetry associated to the puncture comes from. And you have 2n plus 6 fields in that gauge theory description, and this give rise to the 2n plus 6 moment map operators that we have in that picture. Now, in fact, there are more, like by tuning the holonomies, when you compactify on a circle from 6 to 5, you can have more than one gauge theory description in 5 dimensions. as discussed by these authors, also already 5 years ago. So for example, you can have a USP to N gauge theory or SU2 to the N gauge theory, which you note for N equal 1, for the E string, all of them are the same, SUN plus 1, USP to N and SU to N, but they are different for higher N. And the statement is that this SU2 minimal puncture that we get is obtained by partially closing a USP to N maximal puncture down to SU2. Okay, it's a bit fast, but
I have a question in the previous slides. Previous slides. What is this dotted orange square? 2?
It's just that this is a maximal puncture and this is a different notation for minimal puncture.
Okay, okay, thanks.
That's not a deep symbolics. Okay, so now we can play exactly the same game. We can S-glue things together by identifying moment maps, or we can phi-glue by introducing here a 2n plus 6 plot of chiral fields and combining things together, playing exactly the same games. And for example, we can S-glue some number of these trinions together to form a torus with minimal punctures, and use Seiberg duality to obtain this generalization of the wheel. Now we cannot glue these SU2 punctures together because they are minimal punctures. They are not the 5D gauge symmetry, so we cannot just glue them together. So we obtain a theory which corresponds to a torus with a collection of minimal punctures, and you can ask whether this satisfies certain dualities and so on, and you can have a lot of fun with it. Now, one thing I want to mention that although you have a collection of minimal punctures, here something interesting happens. So the basic claim is like that. So we have this collection of we can have a surface with a collection of minimal punctures, and the theory has some conformal manifold. And what we claim happens is that at some corner or some cusp of this conformal manifold, a collection of n such minimal punctures can combine together into a USP to n maximal puncture. Okay, so we have these 3 types of maximal punctures that we can have: SUN plus 1, SU2 to the n, and USP to n. We have an SUN plus 1 maximal puncture in the definition of our theory. We have a collection of SU2 minimal punctures, and the statement is that these minimal punctures can combine to USP to n puncture, not into SU2 to the n puncture, but into USP to n puncture. And this you can check, for example, by comparing anomalies and so on. And once you understand that, you can actually claim that you have a trinion. If you take a sphere with 2 maximal SUN plus 1 puncture and n minimal SU2 punctures, this is also a trinion with 2 SUN plus 1 punctures and 1 USP to n puncture. And now from this trinion, you can glue any genus G surface together, like we did with the E string. For the E string, this n is equal to 1, so this statement is not interesting. It becomes interesting only when n is bigger than 1. Okay, and you can do that, and you can S-glue these trinions together to form a closed Riemann surface. You get these types of anomalies, which you can match with 6D predictions on compactifications of minimal D conformal matter with no flux. You can phi-glue things together to obtain, for example, on genus G equals 2, these types of anomalies, and you can match compactification of these 6D theories with some value of flux. So the trinions have this type of flux associated to them, to each one of the trinions. So this is the flux associated to the trinion, not to the genus to surface. And again, you can see the expected symmetries appearing. SO4n plus 12 is broken in general to SU2n plus 4 symmetry that you see in the Lagrangian, and some and 3 U1 symmetries, 1 U1 which is here, and the cartans of these 2 U1s. And the statement is that when you glue things together, you get the expected enhancement of symmetry, which you can check in the index. Okay, so now let me come to this point that I promised before about Intriligator-Pouliot duality. So you can do this as gluing, and you can again study this pair of pens decomposition duality, but now with general n. So the statement is like this. So you have these minimal punctures, and you can exchange them. Now, as I said, the n equals 0 case is a bit singular because this is a D3 compactification, which is a bit outside of this general sequence of theories, but you can ask yourself what happens for n equals 0. So for n equals 0, the maximal puncture symmetry is SU1. In general, is SUn plus 1. So it becomes SU1, which is just no gauging. It's just gluing things with a superpotential. And each one of these blocks, trinions, becomes SU2 with 8 fundamental chirals. And this duality relating these two pair pairs of decomposition by exchanging these two minimal punctures is simply the statement of Intriligator-Pouliot duality. Intriligator-Pouliot duality for SU2 when n f equals 4 is like Seiberg duality, but it's not self-dual when you just flip the mesons. You also need to flip the baryons. Okay? And you can apply this duality on these two SU2 gauge nodes, and you get the duality which is drawn here. So if you wish, this more general pair of pairs decomposition duality is related to this higher rank generalization of Intriligator-Pouliot duality, okay? Which again seems to be a novel one. Maybe being smart, you can relate it to known dualities. At the moment, I don't know how to do it, except for this degenerate n equals 0 case. Okay. So let me make like couple of final comments. And again, if I can stop here, or I can continue for like 5 to 10 minutes more.
As you want, as you want.
Okay. Okay, let me continue since you are so nice. So let me discuss how the Seiberg duality fits into this picture. So the usual Seiberg duality of SUn plus 2 with 2n plus 4 flavors is the statement that this theory is dual to itself. To the same theory, you need to conjugate all the symmetries but the baryonic symmetry, and you need to add gauge singlet operators which flip the mesons. So this is the statement of Seiberg duality. So you can try to understand what this duality means in this geometrical language. So we conjugate the SU2n plus 4 times SUn plus 2 gauge symmetry that we have here. And you can look on the fluxes, what happens to the vector of fluxes. So we associate this flux to this theory. We conjugate the mesonic symmetries, but at the for the mesonic moment map operators, the flux is 0, so nothing is done there. For the baryons, when you do the computation, what happens actually, the two baryonic symmetries are exchanged under this conjugation. But since the flux is the same for the two baryonic symmetries, again, the flux stays the same. When you conjugate these mesonic symmetries, you conjugate the symmetries of the moment maps. So the type of puncture is changed, but then when you flip the mesons, you flip the mesonic moment maps, so you bring back the punctures to the type you had before. So in this geometric language, the operation that you do in Seiberg duality of conjugating the symmetry and adding the mesonic flip fields doesn't do anything to the geometric information. So you basically apply a while group of SO4n plus 12 on the vector of fluxes, which keeps it invariant. And you keep the punctures invariant. You conjugate and you add the flips, but the punctures stay the same. So if you wish, this is an interpretation of Seiberg duality, why you have Seiberg duality in terms of this language. Okay. So one last thing I want to mention, and then I will stop, is that actually, although I presented the story as having a random fact and trying to understand it, there is actually a systematic way to understand this trinion that we obtained here. So a way to do that is to understand tube theories for general D-type conformal matter, and then study flows between different types of D-conformal matter in 6 dimensions and subsequent flows to 4 dimensions. I will not go into any details here, but for example, if you start from tube theories with the SU2 to the n symmetries, you can obtain such a trinion for an E-string theory doing this procedure. This we did with the Viatar half a year ago. So you get completely different looking trinion. It has 3 SU2 symmetries associated to the puncture, these SU2s, and U1 epsilon, which we claimed enhances to SU2. So there are these different types of trinions with different types of fluxes and punctures. And now you can play this game of building a closed Riemann surface starting from these 2 different types of trinions. And this gives you another types of dualities. For example, if you take this Technion and glue two punctures together, you obtain this type of a theory. With the other type of a Technion, you obtain this type of theory. And again, analyzing things carefully, these two theories should be dual to each other. It's a bit surprising duality, but again, as far as we check, it is correct. And if you wish, this duality follows from 5D duality between this description and this description in 5 dimensions. Okay, so let me finally summarize and make some comments. So, so what I have argued today, that SUN, SQCD in the middle of the conformal window is related to compactifications of minimal D-type conformal matter. And you can read these other comments that we have emphasized during the talk. One thing that I want to emphasize here is that there are these various types of dualities, which like pair of pens dualities and 5D dualities that turn to 4D dualities, as I mentioned in the end. But also there are these dualities which are related to the action of the Weil group of the SO4n plus 12 global symmetry of the 6-dimensional theory, which gives rise to many interesting types of dualities and adds another layer to all of this discussion. Okay, so there are these points that I emphasized during the talk, so I will not repeat them here. And let me end with this more philosophical outlook, which I will not read out loud. So thank you for your patience.
Thank you. Any questions?
Shlomo, hi.
Yes.
Sorry, no problem. You can go.
Yeah. I wonder, can you generalize this to higher rank of E string, for example?
Yes, it's a good question. The answer is I tried, but I couldn't. So there are two things. So one thing is whether you can do you see the slides?
Yes.
Okay. So you can ask, you can try to guess, how do you generalize this to higher rank? And I tried and I could not make it work. Maybe there is a generalization, I don't know. Another thing is that you can try to come up with this type of flow argument that I did not review here at all. For the E string, in a paper with Matteo, Sara, and Gabi, we understood the tubes, the two punctured spheres. Mm-hmm. So the question is, can you lift this understanding of the tubes to understanding of three punctured spheres by some kind of a flow argument of this type, to which I very implicitly allude. And I don't know of any such flow, but maybe if you are very strong in this 6-dimensional physics, the point is like that. If you find a 6D theory which flows into E string theory, higher rank E string theory, and you understand the tube theories of this generalization of the E string theory, then you might be able to derive Technions for the higher rank E string theory. So that is a way to go, but I don't know how to do it explicitly.
Okay, thank you.
I have a question on this same slide, actually. So the 5D theories here, I didn't understand the connection is through a compactification from 5 dimension to this 4D theories, or how does it go?
Okay, so
because they have 8 supercharges, these theories. So
yes, the 5D theories.
Yeah.
So you're asking why supersymmetry is broken in 4D?
Yeah, basically, yeah.
Yes, well, it's broken by the boundary conditions that you put on the punctures and by the fluxes.
I see. Okay, and one more point: the dualities that you get in 4 dimensions, they're to be understood as infrared dualities. Is this the statement?
That's right. Some of them are conformal dualities, but some of them are, like, in generality, they typically, since you have a Lagrangian, and this Lagrangian typically flows, these are infrared dualities. But say here, this is a conformal theory. This is a conformal theory on the nose. It doesn't flow. Mm-hmm. So in this case, you can do different pair of pens decompositions, and you can actually have conformal dualities. Mm-hmm. But in general, you get theories which flow. And then you get infrared dualities. You can maybe think about them like, you flow to some, you have two descriptions that flow to the same conformal manifold, but to different points on that conformal manifold, and maybe to 2 dual points on the conformal manifold. But it's like both of these points are strongly coupled because you flow. Okay, but in some cases you get conformal manifolds which pass through zero coupling, like here. So they are weakly coupled, and you can claim that there are some dualities which take this weak coupling region of this conformal manifold to a strong coupling region. Okay. For example, if you take a genus 2 version here, there is this theory I have drawn in the end. Okay, so there is this theory which corresponds to torus with one puncture for the E string. So you can glue two such theories by gauging an SU2 symmetry. And you will obtain an SU3 square gauge theory, but with a symmetric field for both SU3s. And if you do the analysis, there will be 10 flavors for each one of the SU3, which is different from the SU3 with 3 bifundamentals that we had before, and nine fundamentals for this each SU3s. Both of these theories are conformal, and then you have an example of a conformal duality. But typically you have an IR duality, like here, this is an IR duality. Both of these theories flow. They are not conformal.
I see. Thank you very much.
Shlomo, I remember that in one of your paper, you also have the quiver with mixed USP SU that describe the D-type conformal matter, right?
That's right.
Do you have also example here?
So that's a very good question. So again, we could derive this type of a trinion by starting from those type of tubes. Actually, in one case, for this particular type of flux, which is relevant here, we can start from SU type of tubes that we have there, and we can derive by these flows starting from 6 dimension these trinions. In principle, we didn't do it, but it's clear that it can be done. And then, you know, once you have some types of maximal punctures, you can turn them into others. If you have these types of tubes, say SU USP, you can, you know, turn an SU puncture into a USP puncture. You can start from these tubes directly and try to see what you get directly by doing these flows. I don't know what you will get. My guess, naive guess, would be that you would get something more complicated, since you cannot get anything simpler than that. So we started from SU2 to the N with Aviatar for some reason, because we thought SU2 groups are simpler than SUN groups, and we got this complicated trinion. And if we had started with SUN plus 1, we would have gotten this one. So maybe my intuition is wrong. So if you start from those tubes, you will get something even simpler than that. But I don't know. Does this answer your question?
Yes, yes. Thank you very much, Shlomo. Thank you.
Any other questions? Okay, if not, let's thank the Shlomo again by some method. Oh, before we end the recording, I have some future announcement for future schedule. Next week, we schedule the talk by Sabyok John, but he was in Korea last week, but he moved to the US now. So next week, we will have the talk at the 9 p.m. in China time. And I think 6 p.m. in the, I don't know, some evening in the European time, maybe. And also last week we originally scheduled the talk by Nishinaka, but because of the strike, we postponed his talk, and then he cannot enter the university now, so he wants to postpone his talk to July. So that's the schedule for this seminar series next week and for last week. And we will stop recording, and we will move on to some informal discussion. So maybe Shlomo can answer more informal question. Okay.